Okay, so welcome to part two of this discussion of the fourth lecture of the series. We're going to look down here at causality, light cones, proper time, and geometry. We've learned about Lorentz transformations now, and we're ready to do some and derive more properties of Lorentz transformations and try to understand the space-time geometry underlying Minkowski diagrams. So we've emphasized that these Lorentz transformations, they're written right here, how to transform space-time measurements from one inertial frame to another. They're symmetries of space-time, right? They relate measurements between inertial frames, but inertial frames are all equivalent, right? And so these can be thought of as symmetries of relativity. That's a productive way to think about it, and it's going to help us as we do more sophisticated examples and turn to electrodynamics. Well, the first thing we want to understand are what quantities are invariant to boosts. So we have a symmetry, okay, and there's a symmetry of space-time. Well, I might take an analogous problem, which might just be Euclidean space. And I might ask you, what are the symmetries of that space, three-dimensional Euclidean space? Well, for example, you can measure the distance between 2 points, okay, and that's a physical, geometrical measurement. It doesn't depend on how you oriented your axes. So it's invariant to rotations of the x, y, and z axes, okay, and that tells us a lot about rotations. That has that invariant, which is just given as x squared plus y squared plus z squared. That's unaffected by rotations. Now, what's the equivalent thing in Minkowski space? Okay. Well, so we have to think about what's invariant in Minkowski space. Okay. Well, that's a topic we've hit several times by now. Okay. The invariant thing in Minkowski space is the speed of light. For example, if I have a light ray moving along the x-axis in a positive direction, I'm going to see that light ray unaffected for any boost in the x direction. I always see the velocity c. And then if that light ray is pointing in the other direction, minus x, it'll do so with a speed of minus c. Okay, and so that world path in the other direction is going to be unaffected by boosts as well. So I found in Minkowski space two invariant coordinates, okay, which really characterize the Lorentz transformation as we've discussed it. So the answer is, what quantities are invariant to boosts? Well, light rays. I can take the paths x equals plus or minus ct. It becomes x prime equals plus or minus ct prime under boosts. It preserves its speed. It preserves its form. So therefore, instead of writing the Lorentz transformation in terms of x and t, why don't I just write it in terms of these quantities I call x sub plus minus, which is equal to x equals ct plus x, or x minus is equal to ct minus x. Okay. If I use these coordinates, then they're going to be preserved under boosts, right? Okay, if I have a light ray moving to the right, it's going to be moving to the right at the same velocity in any of the frames. Okay, it's an invariant direction. So in other words, if a Lorentz transformation hits this world path, it has to reproduce it. Okay, because that's what this says. X is equal to ct becomes x prime equals ct prime. It reproduces it. Okay? So it's an eigenvector of the Lorentz transformation. We don't have to do any algebra for that. We can just think it. The algebra I'll have to do is to figure out what's the proportionality when I do the Lorentz transformation. Okay? I know that x equals ct will go into x prime equals ct prime, but that doesn't tell me if there's also a change in scale, and we'll have to take a look at that. But we'll read that off. But at least I know the directions of the eigenvectors, and that's really the crux of the matter. So with that insight, let's do the calculation without any bias. Okay. So I just write down, okay, my Lorentz transformations. Here they are, right? Okay, and I'm writing things here with the dimensions the same everywhere. So I'm putting C next to T and C next to T prime like that, and so beta is V over C. That's a standard notation. You'll find it in the textbook and in lots of different textbooks. So now all the dimensions are carried by CT and X, and gamma and beta are dimensionless. Okay, so now I claimed, okay, that a light ray moving to the right is going to be continue to be a light ray moving to the right. So how can I see that? Well, I mean, I just take the sum of these two, right? I was saying that x plus ct is a special variable, and I was saying that x minus ct is a special variable. So let's take the sum of these two. So I take the sum of these two equations. I get this as the left-hand side. This is the right-hand side, ct plus x. In front of gamma, I get ct plus x. Okay, so I pull out ct plus x. I get a prefactor, which is this. I remember that gamma is 1 over the square root of 1 minus v squared over c squared. I plug that in, and lo and behold, I get exactly what I said. Okay, that coordinate transforms into itself, and there's a change in scale. This is called a rapidity. Okay, and we'll discuss it later. Similarly, I do it for the other light cone variable. Okay, and and just do the arithmetic. You'll just change the minus beta to a plus beta, and the plus beta to a minus beta, and it goes through just arithmetic. Okay, so now you've managed. You've taken the Lorentz transformation. It's a symmetric 2x2 matrix, and you wanted to diagonalize it, and you diagonalized it by thinking about it. Okay, and then you confirm that it works, and now you've got your answer. So we introduce this prefactor, which occurs here and here. We call it e to the eta. We'll see why we write it in exponential form in a minute. And we call eta the rapidity. So e to the eta is equal to this. I guess I chose this one as the definition of rapidity, like that. Okay, and so x plus is equal to okay. Is equal to e to the eta x plus prime. Okay, and x minus is equal to e to the minus eta x minus prime. I'm writing the two equations there in a compact notation, and I think you're all familiar with that. Just associate the signs as shown. Okay, so that's the Lorentz transformations again. Whereas the matrix structures disappeared because we've diagonalized it, and doesn't look so intimidating anymore. Okay. But one of the first things we note from it, and that's really the point of this exercise, is that now I can read off a quadratic invariant in space and time that's invariant to boosts. Okay? For example, looking at this, I see that x plus is enhanced by the same amount that x minus is diminished. So if I take the product of x plus times x minus, that's unaffected by Lorentz transformations, right? The e to the plus eta times e to the minus eta gives me 1. And so this is, I calculate the product of the light cone variables in one frame. I get it the same in the other frame. This stuff cancels out. Okay, and so I learned that the invariant is this light cone variable times this light cone variable, and then writing it in terms of t and x, I see it's this combination. Okay, so I learned from this exercise that the invariant length of Minkowski space is ct squared minus x squared. Sometimes when I talk about it, I don't like to say c all the time. I'll just say t squared minus x squared. Put the factor c in there to get the dimensions right. And so we'll always use this notation. S squared is equal to c squared t squared minus x squared, and notice the minus sign. It was clear from the Minkowski diagram that the plus sign wasn't going to give us an invariant under Lorentz boost, but the minus sign does the trick, as we just have verified over here. I write this as s squared, but be careful with it. You see, it's not necessarily, it's the right-hand side is not necessarily positive, but this is conventional notation, and so be it. So we learn this is going to be the metric of space-time. The metric of space-time is not going to be like the metric in Euclidean space, which is positive everywhere. Okay, it's pseudo-Euclidean. Okay, in the sense that there's a minus sign here. We have to be careful about it. Okay, in our algebra, but physically we understand what it means. Okay, it's just a reflection of the fact that the speed of light is a constant in all these frames. So here it is written down here, but I really should include the other spatial coordinates. Okay, y and z. The other spatial coordinates have just been invariant under the boost, and so I can just add them back in here. But now I can write it in a four-dimensional notation as s squared is equal to c squared t squared minus the vector r squared, which is r squared is x squared plus y squared plus z squared. Okay, so I'm dealing, with a vector in 3 space and time as well. I have a four-dimensional space. It's pseudo-Euclidean, but I'm going to call it pseudo-Riemannian in anticipation of general relativity. Okay, so let's think about s squared a little bit and understand the geometry that occurs in Minkowski diagrams. And so for general purposes, I'm going to imagine that I have an event P1, which is labeled here, and another event P2, which is labeled there. Now I'm really interested in the invariant interval between them. So delta t is the difference of the t's between these two events, and etc. Okay, that's what's interesting to me. I'm always interested in the differences of times and space between particular events. Okay, and so I'm interested in delta s squared given by this formula. This formula, of course, is invariant under boost. It's okay. Just by the derivation that we've already given, and this is the metric of Minkowski space. In some of our cases, we'll imagine that delta t, delta x, delta y, delta z are differential, are infinitesimals, and then we'll write this in an infinitesimal form, and we'll talk about the metric of the space-time. So this is important, and the metric is boost invariant, of course. Okay, it's a physical form. Okay, now Minkowski diagram splits off into different segments conditional to whether delta s squared is positive, negative, or 0. Okay, if delta s squared is 0, okay, then we know what that is. That's a beam of light, right? In that case, ct squared is equal to r squared. That's a light ray moving from point P1 to event P2. That's a light-like interval, I'll call it, a light-like interval. And so I've labeled that as class 1, and here are 2 light rays shown on my Minkowski diagram, and they're labeled by 1. Now I might have instead the 2 points P1, which I'm taking at the origin in this picture, and then P2 anywhere up here. I might have them related by a delta s squared, which is positive. That's therefore called a time-like interval. The time bit of the calculation is bigger than the spatial bit, so delta s squared is positive. Okay? Well, if delta s squared is positive, then of course those points are causally connected. And you see that in the picture. I can send a signal at less than the velocity of light and connect the origin to any point in this forward light cone. Okay? And similarly, if I have a point in the backward light cone, it can communicate to the origin with a signal which goes at less than the speed of light. So that's the meaning of a time-like interval. If I have a point P1 and a point P2 in there, time-like connected, you see the 2 points would be here and perhaps here. I can always find a frame in which those 2 points occur at the same point in space, but at different times, right? Because I can draw a t prime axis through them. And so they could be like the ticks on a clock. They're causally connected. Now, if delta S squared is less than 0, then it's called a space-like interval. And of course, I cannot connect the points by a physical signal, and so they're not causally connected. Okay, I promise you that causality and locality are going to be more and more important in this course, and now we're setting ourselves up to think in those terms. So region 3 is shown in the Minkowski diagram relative to the point 0. And now if 2 points are space-like, then I can find a frame in which those 2 points occur at the same time, right? If I have a point 0 and a point here, I can take my axis x prime to go through them, okay? And so I can find a frame in which they occur simultaneously. And then also, a little more interesting, is that if they're space-like, I could find frames in which their time ordering is not unique, okay? I can, if one of the points is here and one point is here, I can take an x prime axis below it, and I can take an x prime axis above the second point, and then draw that figure for yourself, okay? And then look at the lines of constant t prime, and you'll see that the time ordering of the 2 points is interchanged, okay? But that's sensible. The 2 points are not causally connected, and so their time ordering can be changed by changing frames. I can't do that in the case of the causally connected points, as you can also demonstrate for yourself just by looking at the picture. So go to the textbook. There are lots of problems on causality on these issues. The textbook will ask you, well, what is the velocity of the frame in which the 2 points occur simultaneously, for example? Okay, and you'll calculate v in terms of the position of the points, and you'll do exercises like that to gain an understanding of the geometry of Minkowski space. There's lots to be done, and we'll do them in the recitation sections as well. Let me end with a couple of comments about rapidity. Okay, so rapidity was e to the minus eta is this square root. Looks a little complicated. I can take this equation and solve for v over c, that's beta, and get a formula in terms of rapidity, and notice that it's the hyperbolic tangent of eta. A little bit more algebra, okay, and this is done in the textbook, but it's just algebra, is that gamma is the hyperbolic cosine of eta. And beta times gamma is the hyperbolic sine of the rapidity. Okay. And so I can go back to my Lorentz transformation and now think of it as a rotation in hyperbolic space in the Minkowski diagram. Because now you see when I make these replacements for gamma and for beta gamma, they're replaced by these hyperbolic functions like this, and I can view that as an analogy to a rotation in Euclidean space as a rotation, but now in hyperbolic space with a metric which is a pseudo-Riemannian metric, a metric that's not everywhere positive. Okay, but you see in the case of a rotation in Euclidean space, I would have cosines and sines here, and a plus minus difference. Okay, and again in the textbook that analogy is drawn, and we discuss it. The last thing I want to do is why is rapidity? Why did I emphasize rapidity? Well, rapidity is awfully useful in high energy physics because rapidities add under boosts, right? In relativity, velocities suffer a very nonlinear transformation under boost, but rapidities do not. And that's okay, and that's easy to show that because when I make a boost from s to s prime, my light cone coordinates transform like this. Then if I make another boost from s prime to s double prime, okay, through a rapidity of eta 2, then my light cone coordinates will transform like this. Okay, so that's the case. And so I can then look at the composition of those two boosts and go from s directly to s double prime, because I can replace x prime by x prime over here and go directly from x's to x double primes, and you see how that works. It just becomes this equation, the prefactors multiply, so the eta's add, and that's the point. So the composition of the two boosts gives me an eta 3, which is just the sum of the etas of the two boosts that made it up. Okay, so rapidity has a simple linear transformation that velocities had in Galileo's world. This is very useful in high energy physics. If you do kinematics of high energy collisions, the rapidity variable is very important. And check out the supplementary lecture number 7 in the website Relativity Doctor that accompanies the book for a discussion of rapidity and a discussion of kinematics that make this variable so useful. So I think I'll end the discussion there, and next time we change gears a little bit, and we ask whether we can make dynamics, the generalization of F equals ma, consistent with relativity.